morning and welcome to my presentation on applied robotics. My name is Jack Burnell. I'm a systems engineer at Sundance, and today I'll be taking you through how we've increased the processing capacity of a multitude of robots in a multitude of different environments using our VCS and VCS-Jr computing systems. Sundance business. Sundance was established in 1989 by Fleming Christensen with the idea to create high-performance processing PCBs for computing, with both in-house design and manufacturing. Sundance is a Xilinx Alliance partner with 5 certificated FPGA programmers, allowing us to make adaptable, reusable circuit boards using programmable field gate arrays. A quick overview of what we will be looking at in this presentation. First, we'll be looking at the VCS system, which is a PC 104 standard Linux stack composed of 2 main components, mainly the EMC2 board and the expandable I/O board on top, the FM191 and the FM192. Then afterwards, we will look at the VCS-Jr system, which runs on an Ultra 96 platform with a Robo 96 I/O expandable card on top. Then we will look at the RAI project and how we are using that to increase safety and accessibility in mines. Then we will look at Edge AI on the FPGA and how we can use that to increase the processing of machine learning on low power systems. Then we can look at AWS, which is what we use to increase our workflow and our efficiency in the workplace. And then we will look at IROS and ROS World, which are 2 conferences that specialise in robotics and especially the ROS operating system. What is the VCS system? The VCS system is a Linux stack that has a Zinc FPGA ultrascale from Xilinx. This means that we were able to remove traditionally CPU heavy processes such as machine learning or such as heavy math algorithms onto the FPGA, allowing us to be as efficient as possible with the lowest latency that we can possibly have. This allows us to have a level of efficiency that is not possible with a generic GPU that you get on some standard boards such as Jetson, with higher bandwidth and lower latency. Two separate demos of the VCS system. One is running autonomous driving and object detection around a robotics lab at Nottingham University, and the second one is where we have taken a camera dolly that traditionally is used by human remote control, and we have made it autonomous by making it follow the green ball. The RAI project is a project funded by Innovate UK, and it aims to implement autonomous survey geotechnical conditions during normal unproductive periods. This means the period straight after a blast that happens in a mine, the robot is able to go in and check whether it's safe. This also means that the robot will be able to tell the miners if they are able to go in early or whether they need to leave it longer. This also means they'll be able to detect whether the actual roof itself, the pitch, is correct, because this could lead to irregularities that could cause the mine to collapse at any point, and it really takes the emphasis and the safety into consideration when it comes to human mining. This is not instead of miners, this is to go alongside as a companion so that it increases the safety and lowers the risk to miners that are going inside of the mine at any one time. As part of the RAI project, we have developed the VCS-Jr. Now, the VCS-Jr doesn't run on the standard Dennis robot that we use for the RAI project, which is a huge 100-kilo robot. This is used for the smaller 3D printed robot that we have called the Dennis Jr that we will talk about further on in the presentation. Now, for the Dennis Jr, we have created a I/O hat on top called the Robo 96. This means that you are able to utilise battery power for the Ultra 96, giving it true mobility. It also has a wide range of I/O, including servos, GPS, terminals, and also motor drivers. We also are developing a compatible Xilinx Vitis toolchain library for it, so that it is able to directly link to your FPGA block diagram. It works alongside the main kind of distributions of Linux, i.e. Ubuntu, Debian, Red Hat, and CentOS. It is also ROS compatible and C++, C, and Python compatible. It really means that we are able to kind of push the boundaries of what we were able to do with the Ultra 96 and utilise the FPGA like we usually do on the bigger brother, the standard VCS system. Above you can see a demo of the Xilinx Senior robot. This is running on the VCS-1 system, and this is using autonomous driving to follow across the side of the fence. On top you'll also see a drone which is linked through the Mavlink protocol to talk to the VCS-1 and be able to maneuver directly commanded by the VCS-1 itself. As we spoke about previously, above is the VCS-Jr. This is the smaller brother to the standard beast. This is the Xilinx Jr, and it is used for kind of smaller processes. So, example, we have been looking at using it for stuff like fruit picking, etc. It is a great versatile little robot, and it has the ability to have different attachments to the top. As you can see in the video, there is actually a drone attached to the top of the on top of the Xilinx Jr. This allows it to open the lid, and then the drone is able to fly out and maneuver. Now, why do we choose to use FPGAs over something such as a GPU or a larger CPU? Well, an FPGA to start with is low power, so it's great for kind of robotic implementations because power is always a limit when it comes to robotics, especially when it's mobile robotics. And it also has the ability that it has a much higher bandwidth than a GPU, for example, and this means that we're able to attach multiple I/O to it, and it's able to do kind of simultaneous equations, etc., that mean that we're able to get the most bang for our buck when it comes to the computational power of the system. Unlike a standard GPU, we are not held back by kind of different libraries, etc. So, for example, the CUDA library, we don't have to deal with that. We can either use the accelerated libraries given to us by Xilinx, or we are actually able to program in Verilog so that we are able to get exactly what we want out of the system in pure logic and able to run as fast as possible. The TrueLook book is out now. It is a great look into how you can use AI and low-powered image processing platforms to push the boundaries of your sort of device, whether that be robotics, whether that be kind of finance, kind of a multitude of different things. As long as you need something with a high bandwidth and a low power system, this is a great book to kind of get you started on what you need to look for. Xilinx Edge AI. Now, what is Edge AI? Edge AI is a collection of tools available to us through the Xilinx accelerated libraries that allow us to create AI models, machine learning. So this means this can either be object detection, finance algorithms, a multitude of different scenarios, mostly for robotics and vision, which is what we specialize in, is obviously object detection, etc., like that, optical flow. Now, the four main ones that we can use through this system is Tensorflow, Caffe, Darknet, and IROS. And now I'm going to take you through what each one of them are and how we are able to use them. Caffe is a machine learning framework that is used widely within research, mainly because it has a quick processing time. Now, we can do over 60 million images per day, which means if you are looking for either rapid prototyping or you are looking for kind of a research-based project like you do at a university, and you may not necessarily have the time to spend, a couple of days running the system and maybe even losing access to your computer. Say, for instance, you have a low-power computer and it needs to use as much as possible. This means that you are able to run the system, and it will be done as quick as possible, basically. Darknet is kind of on the opposite spectrum of the kind of system to Caffe. Now, it takes a little while longer for it to train, but it is the quickest. It's the quickest system on the market, with a 244 frames per second with tiny YOLO available through a single neural network layer technology. Now this is because it's able to split the image up into smaller sections and then be able to use a kind of a law of averages to work out, is it likely that there will be something here? Now this is predominantly because of their algorithm. They're able to produce these sorts of speeds. As you use different sort of technologies, you realize that the speed lowers, but this is always going to be the fastest framework for you to use when it comes to detection. Tensorflow is the best all-round AI technology. It is great for people that are just starting out with kind of learning about AI. Because it's run by Google, it means that it has an end-to-end framework. That means it has the availability of multiple language integration. It has the ability for kind of multiple models, pre-trained models, including source code, which means that you're able to see how the model should come out, and then they will give you the data set to be able to test yourself. Now this is great for kind of universities and kind of people, you know, that have smaller, maybe they own a Jetson, or maybe they own a Zincberry, which is a Raspberry Pi with a Zinc FPGA on board. It gives them the ability to be able to kind of not spend all their time trying to learn it. They're able to learn it quite quickly. It also has the ability that you can use the Google Cloud when it comes to running it. You're able to run all kind of everything on the Google Cloud, meaning that unlike with TensorFlow and Caffe, you don't have to lose the ability to use your computer whilst it is running. What is Keras? Keras is a deep learning API that's written in Python that runs on top of machine learning platforms such as TensorFlow. This makes it really easy to implement into previous scripts using Python. This can be used for kind of a multitude of different ways. It can be used in kind of the financial services to create algorithms to be able to detect whether there be wins and losses in stock markets, etc., or it can be used for kind of a standard object detection. Now, the beauty about Keras is the fact that you can literally start with nothing. So you can start with literally a laptop in your bedroom, and if all goes well, without having the need to adopt any other sort of API, any sort of learning structure, you would be able to scale up this computing all the way up to literally a Summit computer, which they use at the Oak Ridge National Lab running Keras themselves. So it is a great kind of API for kind of knowing that once you implement it, that there is quite a high chance that you won't need to switch to anything else in the future. AWS and the Xilinx Vitis toolchain system. What is AWS to start with? It's Amazon Web Services. These are a cloud provider that provide hosted servers and a multitude of different kind of infrastructure that you can use. The main thing that I find with FPGAs, etc., is the pure amount of kind of the size, basically, of these tool chains, etc., is just massive. I mean, Vitis in itself is 150 gigabytes of data without even really installing anything on top. I mean, once you get to a full system and you've got your board files, you've got like your AI models, etc., you're looking at easily 500 gigs. Now, this is an issue when it comes to downloading stuff, because unless you live or work kind of in the city, it means that your bandwidth will be quite an issue. And for a long time for me, living in the countryside, it meant that I would basically have to go and make my lunch while I downloaded whatever I needed to download. Now, with the AWS toolchain, it means that you are basically just using, almost like TeamViewer, you're just looking into the GUI on the server, directly on the server. Now this means when you're downloading anything or changing anything, it's instant. You've got up to 10 gigabit download speeds, or even when we're pushing GPU servers, we've got way more than that. This means that I can download 100 gigs in a matter of minutes, and this really increases the ability for us as a team to be able to work together and be able to push kind of the boundaries of what Sundance is able to do. We've also found with AWS that it means that we can really implement robotic simulators a lot more. Now, the problem with robotic simulators in the past with stuff like Gazebo for ROS is the fact that you needed to have a good computer to get accurate simulation. Now, if a customer comes to us and they don't have a robotic simulator and we design one for them, or we try and push to design one, because from our industry it's a lot easier to start work on a simulator and then move to the actual robot, because to get hold of the robot, quite often they're large, and especially if you take the Dennis Senior in this instance, it is a rather large robot. It's 100 kilos, and well, me personally, I don't have room for that in my house. So it really works out well. But the problem is that a lot of people don't have the kind of infrastructure needed to design this. If you're majority a manufacturing company that happens to have a dolly system that you'd like autonomized, you won't have a computer running state-of-the-art GPUs that are able to do this. Now, using RoboMaker on AWS means it's the best of both worlds. We can host it ourselves, and we can deliver a product to the customer that they can see it working, they can see exactly what they want it to do, we can split the jobs up exactly as we need it to, and it's just a great all-round system to be able to kind of develop customer-facing products for our customers. Above, you will see on the video, it is a video of counting apples. This is a real-time use of the VCS system and shows how a powerful object detection can be used to really push the abilities of a multitude of different industries, i.e. in this case agri-tech. And it really shows how that something that could take a farmer multiple hours can be done in almost a matter of minutes, basically, because they're able to just walk up and down or attach to a tractor and be able to scan the apples without ever having to actually physically count them themselves. The strawberry detection using the VCS system was an academic study done by Samuel Bradenberg. It composes of 5 kind of different sections of kind of what we want to do with robotics, etc. in regards to strawberry detection. We have the fruit classification, so that's detecting whether it is or is not a strawberry. We then have the pose estimation. This is what is the best way to pick the strawberry, because it may be behind some vines, it might be in front, it might be in an awkward position. Then the next step is how can we plan the path? So this is kind of path planning 101. So how can we get from where the arm is at the moment to where it needs to be? And then the next step is grasping. What is the best way to grasp this fruit? So we don't want to bruise the fruit. Now, this may not happen so often with strawberries, but lots of fruits bruise quite easily. You've got bananas, you've got apples, and there's no point in being rough with them, otherwise the customer won't want them, basically. ROS 2020 was a conference done on 12th of November. It was a conference that was sponsored by us at Sundance. It is where kind of all the great minds of kind of robotics come together, and they talk about how we can push kind of the different aspects of robotics, whether that be vision, control, sensors, etc., and the different industries such as agri-tech. This is a sort of a great place to kind of work out where you're going wrong, where you could kind of increase your efficiencies when using ROS, and how best to adapt to kind of new versions of ROS and new ways of thinking within the operating system itself. IROS is more of a kind of an academic sort of conference with the same sort of mindset as ROS itself. It's where people come together to talk about intelligent robot systems and showcase their latest research on what they've looked at in regards to kind of different aspects. One being the fruit picking, the strawberry detection that we showed earlier. That was one that was actually showcased on the IROS conference itself. This is a great one if you're looking kind of more in depth into the kind of academic side of robotics. Thank you for watching my presentation. If you have any questions, please let me know and I will get right back to you.
Hello and welcome back. So we've got a bit of time for a Q&A session now with the lovely people from Sundance. I'm here with Fleming and Jack. And just before we go into the Q&A, they would like to show us a quick video. So Jack, if you want to explain what it is.
Yes, so this was one of the videos that was in the slideshow. It is a video regarding kind of apple detection and counting of apples. It's a really good it gives a really good understanding of how from kind of a low power, battery power solution, you can have a real, basically powerful way of being able to count multiple objects at once, basically. And this sort of FPGA design can be adapted to be used in a multiple of different fields, and not physical fields, different fields of like tech, etc., and just really shows the abilities of the FPGA itself.
So that was a quick visualization of the kind of stuff that they're doing. So if you want to sort of explain what's going on there for us.
Yeah, so this is one of the research projects which we're sort of currently completing, and it's to allow the farmers, this particular one is apples, but it could be oranges or lemons or whatever, to go and identify the potential growth of the apples or the fruit, and also what's happening at the end of it is one of the slides beforehand actually had a sprayer. So what we can do as well is go and do partial spraying. So we can go and identify, is there actually any fruit? Do we have to spray here? And that is done on the edge, so we don't have any cloud connectivity. And that's the main difference of what we're trying to do with the FPGA technology in the agri-tech world is to make it cloudless and very low power. So that's the demo. The next one, I don't know what the next one is, but Jack can introduce that one.
The next one we are going to look at. I don't think it's loaded into the system at the moment. 1 second. It was the one showing how we've been able to adapt the robot to be used on the fly with a previously unautonomized robot.
Okay, good. Yeah, so that's another project we're doing right now where we are using it for going into mines to do surveillance of a mine after a blast. And then the benefit for the mine operators. We don't have many mines in this country, but obviously worldwide there's a big mining potential. And we can go in, we can do a blast, or the contractors do a blast, and afterwards they can go in, send in the robot, do a survey of what kind of damage they got to the environment, and afterwards they can send people in to actually do what needs to be done. It's a very, I think if that's the video I'm thinking about, it's a very large robot. It's obviously very.
Yeah, it's the beast, the 100 kilo or 120 kilo with batteries robot.
And if it is the video I'm thinking about, then it will have a drone sitting on top of it, so it can actually send the drones in further or send up into a crevice or something else. So enjoy.
Okay, so just whilst we wait for the video to be set up, I'm going to start asking some of the questions that we have from ourselves and from the chat. So my first question is just as a more in-depth explanation, how would you say that what you're doing is different from other things in the field, and how would you sort of explain what cloudless AI is?
Well, so we adopted to use FPGAs for our robotics sort of concept, and that was based around a project we did, which was called Tulip, and there was a slide in the presentation about that, and it gave us the flexibility of a lower power platform, which we can then install right on the robot, and then the main attractiveness from electronics point of view is the concept of FPGA as a very low latency control system, which means that when you're doing something and you want it done very quickly, the FPGA can do it without any CPU intervention. The most, I would say, probably 99% of these robotic systems which are out there are typically controlled by CPU and GPUs, and I'll say 100% of them will actually suffer from some sort of a latency issue because of the CPU GPU combination. So FPGA, is our view, is the perfect partner for robotics applications.
So where would you say the future of FPGAs? Maybe what are you looking at? Maybe yourselves to work into in the future, or you believe that this can go into in the future going forward? So
FPGAs had a tendency to be something which most software engineers would not like to touch, because you program in a higher level language, and it's more like a circuit design historically. But and then this presentation is too short for that. But there's a lot of things going on within the community of FPGAs to make it possible to use higher level languages. There's a lot of training going on. There's a lot of material coming out, especially around sort of Xilinx FPGAs and the Sync family, which is combining sort of an ARM processor and the FPGA. And then what is possible now is to be able to program most of it in C, and then actually port it and synthesize it to be able to run it on the FPGA. Furthermore, which is quite interesting and also quite new, is they're now allowing sort of partial reconfigurability, which means that you can have a very small FPGA doing something, and then when you want to do something else, you can use the same FPGA and you can reprogram the fabric, the FPGA itself, within sort of a few microseconds. So for us, it's FPGA for everything, but it's not for the software engineers yet.
Brilliant. I think the video is ready to go, so I think if we cut to that, and then we'll get back to the questions. So now that they've seen that video, do you just want to quickly go through and explain?
Yeah.
On the chat.
So that when that robot comes to us, it comes as just a generic robot that has your motors, etc. And would usually use an Xbox controller or whatever to be able to control it. With regards to how we're able to use the VCS system to be able to kind of adapt it, it means that we're able to push everything through the FPGA and through the CPU, which means that we're able to run on the front of the robot. You can see the RealSense camera, which is collecting data all the time using the CPU, using standard LibRealSense libraries, and then underneath that you've got the FPGA, which is then able to be used for the actual movement of the robot itself.
Brilliant. And I've got a question from the chat here. What is the weight of the VCS platform, and can it be used on a drone application, for example?
The VCS is a bit too heavy for it. It depends on what sort of drone, really. I mean, it's like it's how long is a piece of string in regards to that.
Yeah.
I mean, if you can carry a DSLR camera on top of a drone, you can carry a VCS-1. From a kind of a more adaptable point of view, we do a lot of stuff. So in regards to the drone that's on top of the Beast robot, it uses a protocol called Mavlink. So what it does is it uses a thing called Ardu Pilot, which is kind of a small MCU firmware operating system that talks directly with the FPGA, and then the FPGA is able to beam information back and forth between the two and kind of do calculations with ultra low latency.
Well, I can actually give you the exact weight. It's 384 grams. So it's not heavy, okay? And it takes only about between 10 and 15 watts. So in a drone application, we actually do have the VCS installed in a drone, and there is another video somewhere, probably in the presentation, which is actually controlling a fairly large drone. So the weight issues on drones is typical the batteries. I mean, they are the heavy guys. There's two platforms for the VCS. There's what we sort of develop inside in Sundance, which got a lot of other features. But we also use a smaller platform, the one we call Junior, which is actually like off-the-shelf kind of product, which is even smaller and takes less power, but doesn't have a big FPGA on it. So.
Very, very interesting. I'll look to try and see if I can find that video myself. My next question is, you spoke about ROS. Now, I was mostly wondering why you chose ROS, and what would you say the main differences are between ROS and ROS2, for example?
Okay, so the reason we choose ROS is just because it's a kind of a widely adopted protocol. It's a really, once you kind of have the understanding of it, it's a really simple way to kind of adapt an FPGA to be used in a multitude of different scenarios, because you can then wrap the FPGA in a Python wrapper, which can then be accessed through the ROS protocol itself. Now, in regards to ROS and ROS2, ROS2 now moves one step further in regards to using Python 3 over Python 2, which opens up a whole new kind of set of how can I put it? Basically, a different set of tools that we have available to us. Like with Python 2, you don't have the kind of understanding of bytes within Python 2, whereas in Python 3, bytes is actually its own kind of variable, and it's a variable type, meaning that cuts out a lot of issues that we were having previously with having to use list strings and pulling the information in. Or in my case, I would simply just have to write it all in C and then put a Python wrap around it to use in Python 2, which is kind of really inefficient from a kind of commercial point of view.
Very interesting. That's actually really cool. My next question is, what would you advise to anyone who's not heard of FPGAs before and is interested in getting themselves into the field to work with FPGAs, maybe now or in the future?
Wow. Well, you need to allocate a bit of time, and I sort of obviously quite keen to have Jack involved in this one. I've been involved with FPGAs for a long time, and Jack started with the Sundance about a year and a half ago, and I think I should leave Jack to give some feedback of the frustrations and the joy.
Yeah, I think the main thing you learn when you start with FPGAs, especially when you look into like Verilog programming, etc., is that kind of everything you know from a Linux point of view is a lie, and it's all just a wrapper on wrapper on wrapper. I mean, there is no such thing as TCP/IP when it comes to Verilog. You program everything yourself, which means that you become very kind of understanding of how the different layers work. Like, when you come into Python, you think, oh, I can do everything in Python. Then when you realize you can't do it, you go down another level and you write everything in C. Now, when you get to C and you go down another level, then you start to get into sort of the FPGA world, which then becomes kind of another headache. I find that for me anyway, I always find jumping in at the deep end is always my kind of port of call, and that was kind of what I did at Sundance. It was either kind of sink or swim, really. But there is a lot of kind of infrastructure out there that I know that people use in regards to kind of testing it out, especially in, like, for my case, I obviously had access to a VCS system to be able to test on, use, etc. But some of the smaller chipsets for Xilinx, like the Spartan 3, start off at about £30, etc. And you can start kind of adapting them, and there's kind of heavy documentation on how to program them, etc. And kind of from there, you can use that as a building block to kind of work up to the more kind of larger FPGAs and kind of increase your knowledge of how it all fits together, basically.
Brilliant. Thank you so very much. Unfortunately, this is getting to the end of our time with you. We really appreciate you guys coming around and showing us all of this. It's been fantastic and super fascinating. Thank you very much.